Hi guys. So static rigid body is one specific area where people have to pay attention because it's really important that you score most of the marks, and the most of the marks is going to be scored from marking all the forces and resolving all the forces, and then having a structured method to solve the problem. So I'm going to show you how this problem can be solved. And for any ladders question, you would use the exact same method as I am going to do in this question. And if you use the exact same method, you will not go wrong. The ladder AB of weight W. So I'm going to think, what is weight? Weight is the mass, but with the gravitational element. So weight is measured in Newton. So I don't need to convert this into G. So weight is given as W, Newton. N stands for Newton. So that's the units for weight. So if they say mass, then you would have actually put that as mg. So here it's given as W, weight. So I'm not going to be changing that into, again, G and all of that. Some people, they get confused and they'll put WG, but you can't put WG, it's just W only. Okay, so that has a length 4A, and one end is on a rough horizontal ground. So mark the word rough horizontal ground. That means we have friction. The coefficient of friction is given as mu, so that's not given. The other rests against a smooth vertical wall. So at B is resting against the wall. The ladder makes an angle theta where tan theta is equal to 2. As soon as you read the tan theta equals 2, I would encourage everybody to draw a triangle, and then, because you can't find an angle from here, you mark theta. Tan theta is opposite over adjacent. So using Pythagoras, I can calculate this to be root 5. Because why this is useful is to find what is cos theta. Cos theta is 1 over root 5. What is sine theta? Sine theta is going to be 2 over root 5. So that will help us in the question, because we are not going to find what is theta. If you find what is theta, it's useless because it's not in the exact form. The ladder makes an angle theta. So with the horizontal where tan theta is 2, a load of weight, 4W, weight, again it's weight, not mass, 4W is placed at point C on the ladder where A to C is 3A. So they've given that, and you can see from the diagram at C, a mass is kept, 4W. The ladder is modeled as uniform. The word uniform is really important that you understand that. The weight is acting at the center, which is why I haven't marked it yet on the diagram. So the ladder is 4A, but in the middle, I'm going to mark the weight. So the weight is going to be in the middle. If I move this somewhere here, that's where the weight is, weight W. That's the weight of the ladder. That side is 2A, that side is 2A. And I have a mass at C, at point C. You have another mass kept, or weight, that is 4W. So I'm not going to put G in here as I expressed it before. Weight is already in Newton. And it's at limiting equilibrium. They have said, given that the system is in limiting equilibrium, show that the mu is equal to 0.35. And they have given that A to C is 3C, 3A, the length. So I'm going to mark, if this is 2A, from this to this is 2A. If this to this is 2A, from the center to A is 2A. And if this is 3A, I'm going to say that's going to be A. And therefore, that's going to be A as well, to split that into two parts. Okay, so that's the first thing. I've marked all the weight and then the component at C. Now, if the ladder is resting against B, can I mark the force which is called the reaction force given by the wall to the ladder. And I'm going to mark that reaction as S, or we can put it as reaction at B. And I'm going to mark the reaction given by the flow to the ladder as RA. Let's just put this to A here. And they have given that this is a rough flow. So I know the reaction is perpendicular always. There is no other force there on the wall given by the ladder, given to the ladder. And then a flow is giving a reaction to the ladder. But there is friction here. There is no friction on the wall because it was a smooth wall. But it says here smooth wall. But I have to find the friction. So friction is always acting towards the wall. So friction is always towards the wall because there is a tendency that this ladder can slip off in this direction. So therefore, I'm going to put the reaction, not the reaction, the frictional force to my right-hand side. So that's the friction. I'll just highlight this friction in yellow. Frictional force. That frictional force is equal to mu times reaction. Formula is not given, so memorize the formula. Okay, now, the method that I use, regardless of the question, I would always use up equals down, right equals left, and then moments about point A. So up equals down. First thing I would think, okay, is all my forces up equals down? I can see RA is upwards. Okay, so let's mark RA as upwards. Is there any force facing upwards? There is no force here facing upwards. This is downwards. This is downwards. This is to the left-hand side. That's to the right-hand side. So RA equals W plus 4W, which is RA equals 5W. Then I'm going to do right equals left. So right-hand side, I can see RB. Sorry, that's left-hand side. And then right-hand side, I can see the friction. So I'm going to mark the friction as mu times R. Now, a lot of people can get confused at this point as well. The reaction is basically the reaction here. Because at that point, the reaction is RA. So that R, as a result of the friction is experiencing this reaction. So RA is what that is. So I'm going to mark this as RA here and then RA here so that you don't get confused. Which R am I going to be using? So that's that. And then I can substitute RA as 5W equals RB. Now I'm going to do moments. Now, when I do moments, what you need to think is that every force that I have to be converged perpendicular to the rod. And I'm saying that again, that all forces must be converged perpendicular to the rod. So at the moment, if I'm doing moments about A, I don't need to worry about what's happening at A. So there's two forces there. Friction is there, reaction is there. I'm not worried about that because I'm standing here and I'm going to think about every other force on this diagram. So W is there, 4W is there, RB is there. All these three forces, this force, this force, this force, all these three forces have to have a tendency to rotate towards A. That's what moments. But are they perpendicular to the rod? If it's not, you need to make them perpendicular to the rod. When I say perpendicular to the rod, you have to bring this W to this line. You have to bring that W to this line. And then you have to bring this 4W to this line. Because that's when it's... And then I need to bring this 4W to this line. So I want to bring the 4W to this line. And then I want to bring the RB as well to this line so that everything is perpendicular to the rod. Now there's a problem. The problem is that W, when it's brought to this green line, it's rotating an angle. So it's not W anymore. That green line is not W anymore. It's moving an angle theta, because if this is theta that was given in the ladder, if that was theta, this is theta. So that is W cos theta. And likewise, this is theta as well, because if this is theta, that's theta, that's theta. They are all corresponding angles. So therefore, W, 4W cos theta is that. Okay. Now, we have to deal with this RB as well. Now, what I know about RB is if this is theta, if this ladder is making an angle theta, now if you look at this, it makes this Z angle. So if this is theta, that has to be theta. Now, when RB moves along the ladder, and then this, that makes the 90. So if it's moving this way, it's moving theta, that would be RB cos theta. But I'm not interested in that line. I'm interested in this line. The perpendicular line is what I'm interested in moments. So that is going to be RB sine theta. But people who don't understand this, I would encourage people to remember, if this was given as theta, this is always going to be cos. Anything perpendicular to the rod like this direction is going to be cos. Anything in that direction, but if this was RB, then that's going to be RB sine theta. So just keep it as a standard layout. And now do moments. So the moments is going to be W cos theta has to move 2a, the length 2a. 4W cos theta has to move 3a, and that's clockwise, that's clockwise. How do I know it's clockwise? This for W cos theta has to rotate towards this direction. 4W cos theta has to rotate this way. And now RB sine theta has to move this way. So RB sine theta has to move, altogether there's 4a. So 4a, that's anti-clockwise. Now I've done pretty much everything. I just need to solve these equations. So I'm going to start solving the moments first, this one. So let's start with that. W cos theta times 2a plus 4w cos theta times 3a equals 4a times RB. So I'm just going to take this to this. 4a times RB sine theta. And if you see here, everything had an A. So I'm just going to cancel the A's. A here, A here, A here. So 2W cos theta plus 12W cos theta equals 4RB sine theta. Our ultimate goal is to figure out what is RB, because the weight was given as W. So I'm going to give everything in terms of W. So 2W cos theta plus 12W cos theta is 14W cos theta equals 4RB sine theta. And then if I divide it by 4 sine theta, I can get rid of this 4 and sine theta. So I'm going to divide it. RB equals 14W cos theta divided by 4 sine theta, and which would then become 7 over 2 W but over tan theta. So I'm going to write it as 1 over tan theta. If you want, you can substitute for cos and sine. You can do it like that. So I'm going to show you that way as well. 7 over 2W. In place of cos theta, I have calculated here 1 over root 5. So that's 1 over root 5 over. In place of sine theta, I'm going to put 2 over root 5. And then simplify this. That's equal to RB. So 1 over root 5 divided by 2 over root 5 is going to give you half, which is 7 over 4w is equal to RB. So that's half, and then half times 7 over 2 is 7 over 4w equals RB. Now that I know what is RB, I'm going to put it in here. So RB, I'm applying it into this equation. So RB equals mu times 5w. And then RB is given as 7 over 4w equals mu times 5w. W cancels. Mu equals 7 over 20. Because the 5 goes to the other side, 7 over 20. And then if you solve the arithmetic, 7 divided by 20 is 0.35, which is what the question is asking. So mu equals 0.35. This is another static rigid body question where here it's like a shelf floating up there. So in this question, they said a uniform pole AB of mass 30 kilogram. So this is mass. So for me to understand mass, to convert it to weight, I would do as 30 times G. So 30G. And length is 3, is smoothly hinged. The word hinged is trying to say something. We'll go back to that in a minute. To a vertical wall at one end A. The pole is held in equilibrium in horizontal position by a light rod CD. So there's another rod here holding this upright. The other end D is freely jointed to the pole so that ACD makes an angle 30 and AD is 0.5 as shown in figure 2. Find the thrust. So there is a thrust given here and they want you to calculate the thrust. So what I'm going to do first is I'm going to redraw the diagram so that I can mark all the forces. So in here, I'm just going to draw that. That's D, and that's B, the 30 kilogram. I'm going to mark that, 30G. That's the weight. It's uniform rod, so this side is 1.5, that side is 1.5. This is given as 0.5, so I'm just going to call it 1 here. Although it's not like perfect diagram. Let's just mark it here a little bit so it makes more sense. Being there, so D there, A here, and this makes 30 degrees. That's all they've given. Now, they have said that it is hinged. The word hinge is trying to say that you go and then screw this to a surface. When you screw something to the surface, what happens is the rod or the beam is giving a force to the object or the surface, and then the surface is going to give a force back. But because I have a rod here, I'm just going to keep the force as, let's say, horizontal, and then I'll have a vertical force as well. So there'll be a horizontal force, there'll be a vertical force. There'll be two forces acting at A. Then, that's one thing. Then there is a thrust. Because it's a rod, that rod is going to push this rod to keep it upright. So therefore, that thrust is going to be an upward direction. So that thrust is like an upward direction. And so that thrust is going to be like that. And that's all the forces that I can see in this question. So as I said in the previous question, the method is up equals down, right equals left, moments about A. Okay, up equals down. What are the forces that I see up? The problem is, that's one force. That's another force, which is upright. This is left, but you know this in between force that I have here, that's not vertical or horizontal, that's in between. So I want to bring this vertical or horizontal, and to bring that, I'm just going to use this line, that's the vertical line, and then the horizontal line is somewhere here. So that's the horizontal line. So this is acting upwards, so I'm going to put that as upwards. So if you look at the arrow, all these three arrows that I'm going to mark has to be the same direction. Thrust is a push. So I'm going to keep pushing this object all direction. And that's the resolving part. I'm trying to resolve this line into two parts, vertical and horizontal. T, when it goes to this line, it will become T cos 30. And how do I know it's 30? Because if this is 30, this is going to be 30. And whenever a force is traveling 30 and it's covering this angle to make this line, it will become cos. And this will become sine. So that's going to become T sine 30. Okay. Now I can do up equals down, upwards V, and then T cos 30 is facing upwards as well. That's facing upwards, that's facing upwards. That's equal to downwards, which is 30G. Right equals left. I can see T sine 30 is facing right hand side. And then left hand side, I can see 11. Sorry, not 11, H. That's H. So that's H. And I'm going to do moments about A. If I do moments about A, this 30G has to travel 1.5 because it's in the middle. And then the T cos 30, that has to travel 0.5. But the T cos 30 is facing this direction. So when it moves, it's going to move in this direction. So that's anti-clockwise. This is clockwise. So one of them is clock, one of them is anti-clock. That's plus, that's minus. So clock equals anti-clock. So I'm going to resolve this, which is 30. I'm doing the working here. 30G times 1.5 equals T cos 30 times 0.5. And I can calculate what is T from that, which I'm going to do it in this calculator. So 30 times 9.8 times 1.5. Then that answer divided by cos 30. And then whatever that answer is, I'm going to divide that by 0.5. And I would have 1018 Newton. That's your tension. And then that's your thrust, which is 1018. Then they're asking magnitude of the force exerted by the wall on the pole. So at this point, they're asking what is the force exerted by the wall on the pole, which is this and this. These are the two forces. And to do this, I'm just going to I'm going to put this T in here and then calculate what is V and what is H. So to do this, I'm just going to resolve. Let's see if I can resolve it. So V equals 30G minus T cos 30. And then T, H is equal to T sine 30. And if I put this in the calculator, I should get an answer for V, I should get an answer for H, and then whatever this answer is, you take it, square root it, because that's the resultant force that they're asking. The force exerted, magnitude means they're asking you to find the horizontal and vertical, and then they want you to find the magnitude. Magnitude means Pythagoras. So I'm just going to put this in the calculator. 30 times 9.8 minus that T answer, which is 1018 1018 cos 30, and that's minus 587.613, and then h is going to be t, which is 1018 times sine 30, which is 509. And then if you put that in the calculator, you should get the answer 509 squared plus 587.6 squared, and then square root this answer. You will get 777 Newton.